Hello guys, can you hear the audio properly? If yes, can you please write probably audio's working or maybe a number 1 or 2? Is it working properly? Also, there might be a bit of lag, so we have to manage that also. Alright, I'll lower the music a bit. And maybe tune up the sound. How about that? More or less. All clear. How was your thesis, Mark? I haven't seen it properly, but probably I'll see it this week as I have a submission on the 13th, and after that I'll have a look at it and I can even give you a call. How was your weekend, like you guys? How do you pronounce your name? Moad Lalo. Sorry if I get it wrong. Where are you from? Okay. Nice Mark. We are gonna wait until it's like 6 to 3 minutes, so that everyone gets a chance to come alive. Okay, all right. Morocco. Wow. I've always wanted to go there, but I haven't been able to. It's like next to Spain. I should though. Where are you all guys from? Victor, Mark, I know, Chris, Guillaume, is that French? How do you pronounce this? Guillaume, Duteud. Hi Praveen, how are you? Okay, it's French. Made sense. From Canada. Also, that makes sense. Praveen, where are you from? In India. Brazil. Wow. Victor, that's impressive, man. What are you studying, Victor, in Denmark? Is it design, architecture? Province from Chennai. I haven't been to the south yet. I'm from the center India, from Chhattisgarh. Architectural engineering. Oof, that's a lot, man. Good luck with everything. Do you like it though? Ah, yeah, okay. Yeah, you wrote me Mr. Lonely Sapiens. I really liked your username. Hi, seeing you. Uh, no, no, you haven't. We are just getting to know each other, like on the group. Everyone's saying where they're from. Hello, Tanya. No, we are gonna wait until 6, like 2-3 more minutes, so that everyone's here, and then we can start. It's gonna be pretty simple, I would say, to follow along, and we can even see a bit more advanced stuff. This recording is gonna be available after it is done, so you guys can go back and have a watch. Okay. I'm a bachelor in science, civil engineering, mostly learning design from ground zero. Okay, well that's good, because it's a bit difficult the other way around. Like if you're a designer and getting into engineering, that's really difficult. But if you're an engineer, you're really familiar with a lot of stuff, so it's easier for you to get into design. How's the weather seeing you in Canada? I saw it's pretty cold over there already. Yeah, imagined. Nice. Global warming, man. So who else is here? Um, there was Tanya. What's your background? Yeah, I'm following along, seeing your work. They're really impressive. I have a friend, and he's a big fan of your work also, and your photography skills. They're really interesting. Yeah, I think we should start. We should start. Okay. It's not gonna be like also, as this is my first webinar, so I'm really sorry if I mess it up, or things don't turn out the way they should. Okay. Well. Okay. Yeah. Okay, so first of all, I would like to thank you all very much for tuning in and giving me the opportunity to share what I do and what I love to do. And you guys have requested, a lot of you have requested me to share how I make my Grasshopper scripts and how I come up with these ideas. So I thought it's gonna be a pretty interesting stuff to share, like how I design and use Grasshopper as my primary designing tool, and share the information with you. So yeah, I will start with myself, introducing myself. I'm Aman. I'm from India. Um, I moved to Spain in 2014. I did bachelor's in industrial design, or some of you might know it as product design, here in Madrid. And I've been working as a freelance designer for the past year and a half. Okay. Yeah, so I've been using Grasshopper as my primary tool for the past like 2 years. That's properly. I had another year prior to that, but just a little experience, not much. So why I liked Grasshopper so much? So as you guys know, I don't have a formal coding background, because if you study industrial design, there is no you don't have formation for coding, or learning coding language. So when I saw Grasshopper for the first time, it looked really interesting, but at the same time I was really afraid of it because there were so many cables going left and right, and this dude, and he was just doing flatten and graft, and I was like, how are you gonna even make sense out of that? So yeah, but I persisted, and things are picking up. There's a lot to learn, but we can do it. Like, you know, it's not so difficult. I had the chat open, saying I would like to know where you guys are from. Well, I saw from Morocco, from Canada, Brazil, India, Germany. Someone else joined recently and they didn't tell me. Would like to tell where they're from or what they're studying, or if you have any questions regarding my design background, you can just leave it here, and at the end I'll have a look like it from the chat. So okay, so first and foremost thing, as I was saying, that this software can be really intimidating and might look that it's impossible, but with practice, patience, and persistence, everything is possible. We just have to keep on trying, because if someone did it, you can also do it. It's just a matter of practicing in time. So we are gonna look for the few plugins, which is Kangaroo, which is a simulator for live physics. Biomorph, which I also use a lot. It's a software that was developed by mimicking the biomorpher concept from Richard Dawkins. He's a British biologist. We're going to talk about him a bit later. Anemone, which helps to loop, because earlier in Grasshopper it was impossible to loop a sequence. You had to like hard code Python script or C script. And at the end we have Weaverbird, which is just which is a really powerful mesh editing tool. So meanwhile, I would say to start firing up your Rhino and Grasshopper environment. Yeah, okay, I'll start fresh. You can change your are you guys gonna follow along, or are you just gonna watch and maybe later do it? If you can tell me over here, it's gonna be easier for me to, like, you know, start like doing it fast so that you can later watch it, or you're gonna follow along, so I would explain and go with you guys. Okay, all right. Okay, perfect. Thanks. Okay, so the first we're gonna look at is Kangaroo. So what we are gonna do is like design a thread, like, you know, like it's a rope and you hang it and it just falls or rises. So we can do that. First we draw a curve, a normal curve. Okay, and that's all we need in Rhino, so we can start working in Grasshopper. So we bring the curve component, and we're gonna select this curve. Okay, that's selected, and we're gonna divide it. For now it's 10, but we can maybe later change it from between 1 to 15. Okay, and we're also gonna shatter this curve. We're gonna like break this curve into small segments and exactly where the points are. So we're gonna put the curve is the input, and use the parameters from the divide curve as a parameter for the shatter. So if you don't need to do this, I'm just gonna show you guys. So if you see, it's like, you know, it's shattered like into 10 segments. Okay, perfect. So now we are gonna just use this curve and the points and connect it to kangaroo. So for the first part, we will create a spring from lines. You can find it in kangaroo here, like in forces. Are you guys able to follow along so far? Okay, yeah, I'm sorry, it's a bit if we want to keep things brief, we have to keep on going a bit faster. So yeah, we just connect the shattered lines into connections, and we are going to create unary force. This is just like creating a vector on a point. So for now it's downwards. We're gonna maybe give it a upwards vector. All right, so we have, that's it for creating it. So we have our spring, which are the individual line segments, and we have the points that we have pushed 15 units in the z vector, and we are gonna bring the kangaroo engine, physics engine. We're gonna connect all the forces over here and start the component. So you guys can see it's like going upwards. It's because it's not tethered to any point, and it's just like going upwards. So what we are going to do is take the endpoints of the curve. The endpoint is this and that one, and we're gonna use these points as the anchor points. And now if we simulate it, you can see it's going a bit up. So I think the stiffness is a lot, and we can put a value between 1 and maybe 100. Let's see how it works. Yeah, so if we give like probably somewhere there. I'm sorry if you if you are not able to. Can you please turn on your bifocus? I don't know if I have installed it. No, sorry, I don't have it installed. You guys cannot see it, right? Properly. Because probably you're not seeing the name of the components. Okay, I will, as I told you guys, this is my first webinar, and you're on the Rhino 5. Okay, which component you cannot find? Seeing you? These are the native components. These the curve, point, shatter, and the endpoints. You have to find the spring from lines, or it might be known as spring or something like that. You guys cannot find spring. Can you guys find, wait, spring from, no, this is not gonna work. Okay, you guys can find polyspring, if that's, That's a bummer. I don't know what it is called in Reno 5. I can Google it, but we're gonna lose some time. Don't worry. If not, just you can download later the Reno 6. Anyway, we are gonna use the polyline. And yeah, that's how we have the and you guys can later play on with the values to make it like try different numbers. Okay, so don't worry. I think if you cannot find that component, I can maybe write an email and see how we can do it in Reno 5, and you just switch the component with the Reno 5 kangaroo component. Okay, so we're gonna move on to the next exercise. So you guys have also asked me how I made this one. So I had already prepared a simple one, and as you guys don't have the spring component, yeah, you can download the video later, like you can see the video later for kangaroo 2. Yeah, because this is the rest length in the spring. It doesn't have springs, but it would work with length. Yeah, there is this compatibility issue with and especially when we are switching between Reno 5 and Reno 6. I think it's better we can do this way. I would start making it, and you guys can watch it later. You can email me or text me on Instagram, and I can explain whatever doubts you have regarding personal doubts or with this exercise. So I think it's better like that. Okay, so yeah, in this case you can I'll start the kangaroo component, and like you can simulate something like it looks like tablecloth probably. Like you can even, but it's not exactly the same like the previous one, but the idea is the same. So how I did it, okay, so we're gonna do it rapidly. Okay. We're gonna create a surface component. We're gonna draw a rectangular square surface on Rhino. Mesh to surface. So we're gonna subdivide the surface and convert it into mesh. I'm gonna hide the component, hide the surface, and hide this surface also. We're gonna start like probably with 5 by 5 so that it's easier to follow along. Now we're gonna do simple mesh. So what it, oh no, it's already a mesh, sorry. Yeah, so we don't need to convert into mesh. Okay, so we are gonna extract the edges, we're gonna extract the points, and we're gonna extract the end points, these corner points. I think this might also be a problem in corner, mesh corner. I think it's all, you guys might not have this component also. Yeah, exactly. I also have both Kangaroo 1 and 2, and in the Kangaroo 2 I think there is no. Okay, so Maud says he can use length T in Kangaroo 2. Perfect, Praveen. Length 2 T. Oh, it's the component. Yeah, you can have both. Like I cannot, like if you see here, I have this Kangaroo tab and I have another one. So yeah, I mean you can have both. And we're gonna find the corners. Okay, in this exercise, so we have the 4 edges, and we are gonna do basically more or less the same as previous one. Here we are gonna use the spring component, but if he says you cannot, if you guys don't have spring, Moad says you can use length T. I don't know how. I don't have that component. I don't know why, even though I have both Kangaroo. But anyway, if you guys can have use the spring, you can download the Kangaroo. I think this is 1 and have it. Okay, we are gonna apply the unitary force to the points in the z vector, and we're gonna use these edge points as the anchor points. So we bring the Kangaroo physics engine. I'm gonna put this as a spring, that also the force object. Don't forget to flatten it, because or else you might run into troubles because of the mismatch in the hierarchy of listings. And we're going to use the edge points as anchor points. So I'll start the simulation. You can see it's working. We're going to reduce the stiffness between 1 to probably 100. More or less. And obviously you cannot see the mesh here, so what we need to do is we have to deconstruct the original mesh and reconstruct it later. So what we're going to do, deconstruct mesh, and we are going to use the vertices as the geometry. It's gonna give an error, we have to restart, and we're gonna construct it again using the same vertices, which is the geometry out, and we connect the faces. So there we go, we have the mesh. Any doubts? Do you guys have any doubts so far? Okay, we can continue. Okay, perfect. So how can we make how can we deconstruct individual mesh panels so that we can apply later the effect of like the holes in between these holes. So to deconstruct it, we have to first deconstruct the mesh, and we have to reconstruct using the same vertices, but we're gonna graft the faces. So now we have 25 mesh instead of only one mesh. Perfect. So we're gonna find the center points. We can do that by calculating the normal of the mesh face. So we have the center points and we also have the normals, which is normal is the plane perpendicular to a surface. And we're gonna draw a line SDL which takes input start, which is gonna be the center. I'm gonna flatten it. The normal is gonna be the direction. We also have to flatten it. And the length, the amount of distance we want. So looks something like this for now. And we can scale the mesh faces down. So instead of using only one center, we're going to use the center of each mesh centers. Wait, I have some glitch. Okay, now it works. So yeah, we have the original mesh scaled down by 0.5, but you can change it, like you can put the distance you want, the scale factor you want, sorry. Okay, so now we are gonna move this geometry to the end of the line. How we're gonna do that? We're just gonna use the component move. What we're gonna move, the geometry, and how we're gonna move is, sorry, not the mesh, this geometry, and how we're gonna move it in the distance of the line. So we have it something like this. Perfect. So the last step for the geometric creation is we're gonna loft the edges of this mesh and the edges of this mesh scaled down. So we're going to use the weaverbird component, which is weaverbird face polyline. We have the original mesh, so we're going to have 25 polylines. We're going to use the same component for these. I'm going to hide the previous. Okay. So we're going to loft this and this. I'm going to loft it. That plus that. So we have 25 lofts. Perfect. We're also going to change the type of loft option to straight, because we don't want interpolated loft, we want straight loft. So there we go. We have the loft, and we are going to convert this loft into simple mesh. Flatten. Okay. But you can see these are 25 meshes, and we want only one mesh, so we have to join all the mesh. Okay, so now we have one mesh, and now we can use the components from subdivision from weaverbird. For example, we can use Cardinal Clark, so directly you can see some improvements. Like if we change the values. To better visualize this, I'm gonna custom. Okay. How are we going with time? Oh, okay. So yeah, change the diameter. We can even the distance. And we can change obviously the stiffness, and obviously we can bake and later 3D print it if we want to. Obviously this is not going to be 3D printable because it doesn't have volume, but we can give it volume by using the thicken component from weaverbird. So we have this original mesh. We have this original mesh, and we're gonna input it as this one and give it the distance. And use this as the input for So there you have it. Now you can 3D print it. Perfect. Moving on. I'm pretty sure you guys were not able to follow along, but you guys can watch the video again and try to follow along. It's kind of inverse of flatten. Okay. 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 Graphed. That's a good question. And so basically, it's like one example could be, imagine you have Amazon boxes, and each Amazon box has an item inside. So you have, imagine 5 Amazon boxes. Inside one you have the MX mouse, you have in another box Apple Pencil, you have a Pixel phone. So you have 5 Amazon boxes. So that's saying like there's one item in each list. Now imagine if I have a big Amazon box and I have all the items inside that box. So that's kind of like flatten. So it's like in the same list, in the same hierarchy. I'm sorry, it's not like the exact way to explain it, but it has to do a lot with matching the hierarchy of the list. You can have various levels in the list, and what Grasshopper does is it starts comparing one list to the other. So imagine if it has different hierarchy, so it's gonna try to apply that thing to all of that. So for an example, if I have okay, one curve, I'm gonna copy it various times. Okay, so we have 4 curves like that. So I'm gonna put this curve, and I'm gonna put these 3 curves in one list. So I have 3 curves and 1 curve. Imagine if I do loft. So I can do loft by connecting them together. So it's interpreting this as one list because all 4 curves are in the same Amazon box. But what if I change and increase the hierarchy? Oh. Okay, that's interesting. Yeah, the problem with loft is it accepts all the value in the same input point. Also could be if I have 2, probably. Yeah, okay, we can do that. Yeah, so for example, this one. So imagine there's nothing. All right, so imagine there are 2 curves on the bottom and there are 3 curves in the top. So right now what's happening is they both are being interpreted as one list. So there are like 5 curves. But what if we increase the hierarchy of these curves? So we say graphed. No, I'm failing miserably, sorry. Graphed. And yeah, I would come up with a better example. Anyway, so it's just like matching the level of the list. Anyway, let's keep on going. I'm sorry I couldn't clear your doubt like on the go. I think it's better if I can point to you to a better resource who can explain you properly. So yeah, coming back to the exercise, you have seen this common theme that I'm using. I'm using a lot of simple surface converting them into simple mesh, and then applying the Catmull-Clark component from Weaverbird. So it's, for example, if I want to create a spoon, I can literally just start by
Hello, Neil. Who are you? I am the architect. I created the Matrix.
Okay. So I'm just creating basic mesh faces. I'm gonna join them together. It's one mesh, and then I'm gonna mirror it and join them together. Okay, so it's one mesh. So I'm gonna have a mesh component, and I'm gonna apply thicken command from Weaverbird. I'm going to use Catmull-Clark to soften the mesh. And to better visualize it, I'm going to move it in the axis by, okay, more or less. So as you can see, just by the simple mesh, you can generate pretty cool organic shapes, and you can adjust them on the go. So I'm trying to make a spoon.
Hallelujah. You're my savior, man. I'm a personal Jesus Christ. You get caught using that. Yeah, I know. This never happened. You don't exist. Right. Something wrong, man? And you look a little whiter than usual.
Could be better.
Like
Why not?
So
I use in my Grasshopper exercises a lot of simple mesh, and then use Weaverbird to make it softer. So as you can see, I just designed a spoon in less than probably 2 minutes. Yeah, that's really interesting about Weaverbird, like the mesh relaxation and using simple surface. Obviously, this is not as precise as modeling with the splines and NURBS, but if you are doing something organic, you don't need to be so precise, and you can control more or less the aspect of the shapes anyway. So we can, if we have time, we have not much time, but I'm gonna just show it to you guys. So yeah, this is the example that I was talking about. Like I had curves, just basic curves. I did loft, and you remember I turned the straight sections. So these are like planar surface, no magic, no like special components. I converted the mesh, the surface into simple mesh. It's gonna be better. Yeah, simple mesh. And then I started applying the Catmull-Clark subdivision, so you can get you can design a toothbrush just by basically designing 1, 2, 3, 4, 8 curves. And obviously I connected it to biomorph. Okay, so were you guys able to install the biomorpher? If you guys can tell me on the chat, that would be helpful. Okay, Mark, you were able to install it. Were you able to use it? How many of you are familiar with biomorph? Okay, so I would do a small demo with biomorph. I already have the wait, I'm gonna hide it. Well, right, yeah. This is a file that that is on the public domain. I'm gonna show you where you can download it. And this is a toothbrush that is being designed algorithmically through generative design using biomorph. Okay, probably not this one. So yeah, you can see that I have basically designed a rectangle, another one a bit to the top, and same, like I'm doing the same rectangles. And these are the parameters that gives the rectangle its shape, and we can change it and the whole toothbrush adapts. So what biomorph basically does is we're gonna create a rectangle. You guys can follow along if you want. So we are creating a rectangle of 100. Sorry, we're gonna create it between 1 and 100 to make it drastic. Okay. No, that's too much. Sorry. Let's do it between 1 and 20. Yeah, that's fine. Perfect. And what we're gonna do is we're gonna move it in the z vector by 20. Okay, so we have it here. Perfect. And we're gonna copy it 1, 2, 3 times, 4 times in total. In this one it's 20. In this one we're gonna do it 30. In this we're gonna do it 40. And this 50. Perfect. And we're gonna do a loft between all these 4 rectangles. Keep in mind that the loft component works the way you connect the cables. So if you put this one and this one, so it does that, and this one, so it does that, and the last. So but instead of that, if you connected, imagine this one, but you connected the third one, so it's gonna go directly and it's gonna skip this one, and if you connect it later, it's gonna do some weird stuff. So make sure that the order of connecting loft is in sequence. Okay, perfect. So we have the loft. Make sure in the options menu, right click loft options, convert it into straight sections. Again, the same patterns, simple faces, and you can see how it's changing the geometry. Perfect. So yeah, we have created a domain, and with that domain we are creating a loft, and we can do the same simple mesh. Sorry, we have to close the loft. You can see it's open, it's hollow, so we cap it, cap holes, and it's closed. And now we're gonna use the simple mesh and get the geometry by Catmull Clark. Okay, so we have some weird stone, like river stone like shape, and we are going to use biomorph. Okay, so let's open biomorph. You can find it in utilities in your params tab. No, okay, so I haven't touched. Okay, just confused with the KK2 and for him. All right. Okay. Yeah. So is it the same as Galapagos and Octopus? In a way, yes. Like the way it works, the way it handles genes, the way it handles mutation, but it's not. In Galapagos, you have to give a fitness value, and without the fitness value it won't work. In the case of biomorph, you can also give it a fitness value, but you can also guide it visually. So we're gonna see it how. So the biomorph component asks for genome, the mesh, the performance. That's the thing we have to worry about. Don't worry about the last one. So in the genome, so a genome in this case is whatever information that makes this shape. So all the parameters that gives this shape its value are its genomes. So we're going to connect all the X and Y cables in the component of biomorph. You don't have to worry about the order of connecting it. Let the evolutionary algorithm take care of everything else. So we connected all the X and Y components as the genome, and we have to put this mesh for the visualization. Okay, so that's it. We don't need the performance for now. We are gonna do it in the next exercise. So double click it. So here you're gonna see how it starts. Are you guys able to follow along so far? Or can you guys please let me know? Yep. Okay, perfect. So yeah, again, you double click it and you have the population size, you have the crossover rate, you have the mutation rate. Don't worry, just press the go button. So it's gonna generate 64 new geometries and try to group it depending upon their similarities. Don't worry about this window, the populations window. Go to design window. So here you can see all the variations that it was able to generate using the random starting with a random value for each organism. So you can double click and you can watch it in Rhino surface, or you can also watch all of them together here. Okay, are you guys able to get the results? Sleek. Okay, yeah. The first time I used this component, it was like, because I always found it hard to um, give beauty and aesthetics and likes a number so that I can plug it as the fitness function. But now imagine we want to evolve, or we want to get variation of the organisms that are slimmer. So in this case, let's go, this one is a bit slimmer, this is also a bit slimmer, and we can use these two and we can evolve to generate children based on these two parents. We can even put more. It's not like the sexual reproduction that happens in living organisms. It's abstract way of reproducing. So they're gonna take the value of each organism and try to cross over or average the values and generate the offspring. So we select this one, and let's click evolve. So we can see already we are gonna have a lot more slimmer organisms in the next generation. Let's keep it going for a couple of generations, and you can already see that the slimmer population has already dominated the gene pool, because we are punishing the organisms that are thicker. But even if you say even if you do that, you're gonna always see thicker organisms because of the mutation rate. That's how new information is introduced in a system, in a closed system like this. So yeah, so this is like just the aesthetically. But imagine if you want to follow along, we want to measure how the geometry is based upon a performance value. For example, let's say the volume. Imagine we want to calculate the volume of this mesh. So we get a value. So it's 253. But if we change anything, the value changes too, because it occupies more volume. So we're going to use the volume as the performance metric and do the same. But now, wait. Okay, yeah, sorry. If you connect it with the panel, it doesn't recognize it properly, so you have to connect directly with the volume to the performance. So yeah, if you now initiate the generation, you're gonna see a new tab here which says volume and the value of the organism. And you're gonna also see here, so this has the list and this has the most. Okay, the thing which had like faded but with a circle is the list, and the one with the most color unsaturated and the circle is the most. So we can literally either we can select it here, or we can just say here we want to minimize the value. We don't need to select here the organisms, and we evolve. Again, we go a few generations. So you can see it's going down slowly. So for example, in this, the list has 151, this one. Let's evolve it again. And in this generation, the list has 152. It's like it's starting to get lower and lower. 141. Yeah, I mean, you can obviously it's not always like going down, because with the mutation it might bump up and down, but if you let it happen for a long time, it will get into the lower value. We can just switch, instead of biomorpher, we can use Galapagos. And here you just select all these sliders, left button, and we can just select the sliders. That's a good thing about Galapagos. You don't have to do individually the connections. And use the volume as the fitness. And now here we don't need to, we want to minimize it, and we just start the solver and we just let it run here. So you can see here we don't have the possibility to evaluate each and every one, especially based on their aesthetics. But as you can see, it's working. Like, you know, it has gone through hundreds of generation, and it has already achieved 52, the 42, 33, 28. So like, you know, it's approaching the minimum value a lot faster than biomorph. And that's, you can achieve the same in biomorph, but it's a tedious work, like, you know, to click and click. Here it's going through hundreds of generation in 1 second. So yeah, it has reached probably its minimum. You can even mutate a bit so that it tries to adjust and doesn't get stuck in a local optima. I think that's the minimum it can get anyway. So that's the difference between biomorph and Galapagos. And Octopus and Galapagos are a bit similar. Octopus gives you a lot more flexibility, and it has a different 3-dimension visualization of fitness landscape. But for what I do so far, I haven't experimented it with yet. The node is on the bottom of the component. Wait, how did you add volume? Okay, so to add the volume as the fitness, it's not, you have to do it the other way around. Like you cannot connect from volume to fitness. You have to connect fitness to volume. It always works like that. And you cannot connect the fitness to everything. Like, you cannot connect it here. You have to connect it to something that gives number. You can even connect it to mass addition. Imagine if you summed a lot of numbers. You can connect it there. So it's, but you cannot connect volume to here. You have to connect from fitness. Okay, perfect. Sorry guys, I don't think there will be enough time for the anemone component. I would like to wrap it up a bit faster. We can do this the next week. So before I go, I would like to recommend 2 books that I read, and they were really inspiring and interesting. The first one is Digital Biology from Peter J. Bentley. He's a computer scientist at UC University College London, and this book is really about how this book is actually pretty old. It's from, I think, 2000, somewhere like that. But yeah, it's a really interesting book. Talks about how he tries to simulate biological process in a computer in the era where the computers start getting faster and stronger, more calculations. And the next book is The Blind Watchmaker. So this book, I hold it really close to my heart. I don't know, I think everyone has their really favorite book, because this book was the spark that helped me get into the digital biology, computational design, and how to use natural process to design products in this case, because I was in my third year of my university, and I was reading this book, and that's how I drifted towards that area. And for my thesis, I can show you guys fastly. You can also see that in my Instagram profile. This is my thesis project um, where I designed this plates using my genetic information. It was like, we are made out of genetic information. What if I use the same genetic information to design a product? So that was the whole concept behind the thesis. And yeah, so this book is really this book's gonna be, it has nothing to do with computers and stuff, but I find it really interesting. And you can obviously check out a lot more projects from past projects that I have done on my website, especially on the research tab. Here you can find the ant portrait. This has done with anemone actually, so I think we can do this probably for the next session. Okay, so we can do that for sure. And lastly, you can find free download files in my Gumroad page. It's gumroad.com/creativemutation. Here you have the music visualizer, the mesh grow, and the toothbrush algorithm. The toothbrush algorithm I think when I uploaded it, it was not connected with Biomorph, or probably it was. Wait, yeah, I think it's connected, because I got it over there. Okay, so I think you guys, if you have downloaded all the plugins that I told you, you can download all of these and just use it and play around, and let me know like what else can we use to make using generative algorithms, for example bottles or ceramic vase or I don't know what. So that would be really interesting to know. Yeah, okay. No, the website, I made it, but using Squarespace. It's not sponsored, obviously, but yeah, I made it using Squarespace. That's basic. I try to use Photoshop and have the same kind of portrait, like the portfolio. Oh, my English is really messed up. Yeah, the image for the project, but later it's mixed, so yeah, it's basic Squarespace template and just keep uploading photos. How did you get into reaction diffusion algorithm? Like how I find out about it, or how can we do it? I don't get the question. Okay, yeah. Well, reaction diffusion, I think, was the birth child of Turing, probably. And there is a really interesting reaction diffusion article about for computers by Carl Sims. If you don't know Carl Sims, he's a really big genius related to computational biology and stuff like that, and he explains properly how it works, like, so you can read it, and it's not that difficult. It's just how particles interact with each other, and that's it. And you can assign functions and values. What happens if the particles are more or less, or what happens, the proximity and stuff like that. What else? Yeah, I think that's it. If you have any questions, please let me know, and I will try to get back to you, probably by email or just on my Instagram, and you can write it over there. Obviously, I'm really thankful that you guys made it so far. It's already 7:10, more than what we anticipated. Okay, yeah. But just wondering how to bring it into Grasshopper. Do you? Okay, so there are a lot of ways to do it. For example, with Grasshopper, there is in the Kangaroo, there is one component called sphere collide here. So if we just copy it and use it in the wait, remember the curves we made. Let's see if it works. Points, radius probably 2. And I think I have to use the same. So I have to use it from the same type of Kangaroo. No, it's not letting me. No, you can do that with Kangaroo. There are examples. When I did that, I found it in the Grasshopper forum. There are a lot of sample files, and you can download the files and play around. So, for example, this. Obviously, you don't need to. It's really great that you can understand everything, but it's not always the case. So just try to understand at least how it's gonna be helpful in your case. For example, in my case, I wanted a surface that simulated like desert, sand dunes, and reading about it, I found out that the mathematical formula is reaction diffusion. Obviously, I can spend days studying how it is done, but to move, to make it, I don't need to understand all of it. So I just found something similar in my case and just try to replicate it. So yeah, that's more or less. This is done by custom C script that I downloaded from the Grasshopper forum and edited it depending upon my requirement. So yeah, obviously this was a component from Laurent, the same guy you can see here. He's a genius. Yeah, okay, so I think that's gonna be it for today. Let me know any questions you have or how can I help you guys. Okay, perfect. So yeah, thank you very much for for making it till the end, and hope to see you guys again. It was really fun, and I'm really sorry that I was not able to uh, uh, clear a few doubts or the problem with the kangaroo component. That's the thing. I'm gonna improvise, and next time it's gonna be a lot better. See you guys on Instagram. Let me know how did you like it, any feedbacks you have. Um, so yeah, happy weekend, and thank you very much. Bye bye.